Assalamu alaikum wa rahmatullahi wa barakatuh. Today, we're gonna speak about computational chemistry. So before we go further and explain what's computational chemistry, we need to put some basics concept, theoretical concepts of what's the meaning of computational chemistry, what do we need from computational chemistry, and then we move to we call it experimental. It's not experimental, but we call it experimental. Experimental means, we using the software to produce some experimental data. So in a simple way, we will first explain the basic concepts of theoretical chemistry and computational chemistry, and we will explain what is the composition of these topics. Then we go further and apply these in some kind of software, which is good for beginners like WebMo programs. So what is the computational chemistry? Computational chemistry is as any science of the world, it's built on some components. Actually, it's built on two main components. First component is quantum chemistry, and the second component is a numerical solution using computers. The numerical solution using computers is also based on two basic concepts. The first is a mathematics, and the second is programming, to solve these equations. So we will not go in all these details, but we want to know what do we need from each of these sections in our computational chemistry, and what's the difference between these sections and computational chemistry. The main difference is computational chemistry doesn't go deep in the mathematical concepts and the equations. It hinders itself from being so deep in such mathematics. It actually uses the mathematical concepts, the mathematical modeling, and such concepts to produce what's called an understood physical concepts. So we don't need to go in such difficult details. We will use the programs to solve such chemical and quantum equations, which was so difficult, and we will understand the concept behind such equations. So we don't need to study quantum chemistry, even though we will have some sections explaining some parts of it. We don't need to go further in explaining mathematics, and we don't need also to explain programming, but all these concepts will result in computational chemistry. So computational chemistry needs some basic concepts from all of these topics. You need to know a little bit of each of them. So you get at least understand the basics of what computational chemistry comes from. Computers. So it is a computer way to solve some quantum equations using some programs. The equation itself to be solved need some approximations and need some mathematics. So it's a combination of all these concepts together. What is the really we need to know, the basic need, the minimum need out of all of these things, we will explain in details. So let's go back to the core of the computational chemistry, which is quantum chemistry. Why do we need a quantum chemistry? And what's quantum chemistry is mainly rotating around. In a simple way, quantum chemistry is based on Schrodinger equations. So why do we need a Schrodinger equation? Why do the classical equations is not enough? What's the difference between these two basic concepts, the classical and the Schrodinger wave equations? So quantum is mainly based on something called Schrodinger equations. Of course, there are many other approximations, but what is the new thing that Schrodinger equation will add to us? It actually lead us to the dual nature, which means the particle has a wave character and the wave has also a particle character, which means that the particle and the wave are not two separate things. They are combined together and they have the same thing together, all together with the same particle will have also wave character. This seems like quite strange because particle and wave are used to be different. The particle is something that has a mass and occupies some specific volume, while the wave distributes everywhere. It doesn't have a specific place. It actually spread over the space and gets different intensities over different places because it may decay with the distance. It may have lower intensity as we go far away from a source of light. For example, you get lower intensity when you go farther away. So it has intensity everywhere, but with different amounts. While particle exists in some specific place with some specific mass. The issue is there is no clear difference between these two things when you are dealing with a very small particle like electron moving with a very fast speed in a very small place called an atom. In this case, the electron will behave as a wave more than will behave as usually as particle. So the usual equation used for particle might not be as good to explain the wave character which will dominate in such case. So in a simple way, we want to speak about the wave character of the particle. This is what Schrodinger equation is doing to us by giving us some kind of an equation with a psi, where psi is usually it's spelled wrong. It should be psi, but we call it psi, which is not correct. It's supposed to be psi. So psi, by a simple Google search, while writing a Schrodinger equation, you get a lot of information. So memorizing is never a good way to learn, because if memorizing is that way of learning or it's a kind of education, you might think of Google as a good professor because he knows everything. But you need to understand the basic concepts. This is the main difference between you and the machine. So let's go further. For example, in case of what we are speaking about is the Schrodinger equation, it's composed of the following. It's composed of H, the Hamiltonian operator, and psi, which if combined together result in psi and something new, which is eigenfunction, it's called the energy. So depending on the orbit, depending on the operator you are using, you get different values. So for each value, you apply a different operator. Let's case, in case of total energy, use Hamiltonian operator, you get the total energy, which is E. The most important part in this equation is psi, which comes to explain the wave character. As you can see, it's a wave, the wave character of the particle. So let's have it in a more, deep concept. So let's speak about the difference between the particle and the wave. The particle and the wave have common and different characters. For example, if a particle hits, a wall, it will get, reflected. It will get reflected. So the same case happens in case of a wave. For example, if a wave light hit a mirror, it will get reflected. Another common character is that sometimes when the light passes from one media to another media, its change of its direction goes some kind of a different angle. This also might happen in case of particles. For example, if you use a gun or something and you hit a surface of the water, the bullets will go inside the water, but it must not sure move in the same direction. It might get, reflected a little bit. Sorry, diverted a little bit from its original path. This is what's called the common criteria. So what's the difference between the particle and wave if they have such common criteria? They also have two majorly big differences. One of them is the mass. The particle has a specific mass at rest, because to measure the mass of something, you need to put in a scale. Have you ever seen a rabbit, moving and running, and you weight it? No, you never weigh it like this. You put something on a balancer, you need to make it fixed, not moving, at rest. So to get the accurate measurement of something mass, it have to be at zero speed. So the particle can get zero speed and can get a specific mass, while the wave is always moving. If it stops, it vanishes. So it has no rest mass. It cannot rest. The wave cannot rest. So you cannot get its mass, m0, or the mass at speed 0. It's a big difference. The second big difference is, the light diffraction. For example, if the light tries to pass from a barrier with some kind of a hole, this hole is shorter than the wavelength of the light, then in this case, the light will move out of this hole and goes in different ways, in all the ways. This can never happen in the particle. If the particle meets a hole which is small in size, it will either reflect it or might pass the hole, but also will goes out in one direction. It will not go in many directions. This phenomena is called light diffraction. So the light diffraction is one of the phenomena that distinguish the wave character from the particle character. The issue is that it seems like the wave have some more characters that doesn't exist in case of the particle. This main difference between these two led to a big fights between physicians. How to deal with such situation? Something that have sometimes a particles, some things that have sometimes a wave, and they get some kind of a complicated issue that cannot be solved unless you apply wave mechanics, which results finally to what's called quantum chemistry or quantum mechanics. So quantum mechanics was a physical concept that has been applied in chemistry, resulting in Schrodinger equation to deal with the wave character of the material. So let's move to the next example. So let's move to the most important and fundamental example of quantum in chemistry was a particle in a box. If you put a moving particle, of course, inside a box, it will move from one side of the box to the other, hitting the edges of the box, and moves to the second side. So it will move from here, hit the wall, comes here, move like this, forward and backwards. So it means the particle will exist everywhere with the same probability. For example, here, it will get the same probability as here, and it will never goes out of the box. It will just move, goes back forward, and the speed will remain constant. The speed will remain constant because the kinetic energy of this particle is fixed. This is the classical view of a particle in a box. But suppose that this is not a particle. Suppose that particle has a wave character. In this case, if you put a wave inside some discrete or a specific space, if you fix the wave inside a place, if you put it like in a prison, in this case, it's called a stationary wave. The stationary wave has many solutions. This is the first in energy, second in energy, and so on, has many solutions for energy. Let's take the first one as an example. As you can see, the probability for finding the wave in the middle of the box is a maximum and goes down as we go to the edges. Here, there is no probability to find the wave. Here, the amplitude is a maximum for the wave, and here is 0. This red and blue lines, because the light is composed from electric and magnetic fields, and this is the electric component and magnetic component of the field, this is a different issue right now. So all these issues may be discussed in details in different videos. Now we want to review the issue in a fast process to know What do we need to understand and grasp the meaning of computational chemistry? So we have two different pictures now. One for the particle says that the probability is fixed all over the box, and one saying that if it is a wave, the probability will be different, and if it goes to level 2, the maximum is in this position and in this position, and here we will get 0 amplitude, or what's called node. If you go further, the number of node will increase. So as energy increase, the number of particle increase. For example, here the second level has 1 node, the third level has 2 nodes, the fourth level has 3 nodes, and so on, until you get to a level with so many nodes and so many maximums, next to each other. Seems like everywhere there is a maximum and everywhere there is a node. So as energy goes up, the number of nodes will increase, because in every level you have n-1 nodes. So if energy goes up, number of nodes also will goes up. So you have many nodes, many maximum stacked together in the same place. So it seems like everywhere you get maximum and next to it a node, maximum and next to it a node, means you will get something like homogeneous probability once again. So if energy goes to infinity, we will get some picture like the classical picture out of the wave picture. So we can consider the particle picture is an exceptional case, while the general case is the wave picture. In this case, we will call it the correspondence principle, which means that the classical picture is a special case of the wave case, which is the general case. One more point that I want to be clear here. When we study this example, they always say to us, this is a particle in a box example. I think the label is not correct. It should be said, it should be named the wave in a box, not a particle in a box. Because a particle in a box will behave in the classical wave as we know. Like if this particle has a wave character, so what do you mean? Is there some particles that doesn't have a wave character? As we might see in some examples, if we apply the Pauli equation, we will get sometimes the wave character is very limited for macro scale particles. For large particles, you will get a wave character which with a very minor wavelengths, that you can simply say that there is no wave character, or there is no way to prove that there is a wave character for macro large big particles. So in this case, you can apply simply classical and ignore the fact that if there is any wave equation, it will not affect any of your results. But once the particle is small and larger and small in size and faster in speed, and restricted in a smaller area, then it will not have the particle character. It will behave as a wave. In this case, it should be regarded as a wave in a box, not a particle in a box. In this case, the wave will have the stationary waves that we usually found if we make this standing wave, like if you bring some kind of a fork with a specific frequency, and you make some kind of a tube, and make this experiment, you can find at some specific distances, you get some standing waves. These standing waves have a very strange energy dependent of the box size phenomena. So if we move to the energy of the particle in a box, the energy is equal to n square h square divided by 8 ml square, which means that the energy is dependent on the L square, where L is the length or the dimension of the box, which means the energy of the particle as a wave depends on the dimension of the box itself, which means that if you restrict the material into some kind of a specific space, the dimension of this space effect on the energy of this material. This leads us to what's called of nanoparticle or nanotechnology. So nanotechnology is built on the basic concept of the particle in a box. If a crystal with a size, if you change the crystallic size, of course you cannot change the crystal size. I mean, if you change the way the crystal are arranged, if you change the way the crystal are arranged, if it is arranged in a tube, in a wire, in, if you change it, like make a big crystal, make discrete dots, then the shape of this arrangement will affect the, character and of course the energy of this particle. So instead of searching for a new material, you just change the arrangement of this unit cell. So you change the dimension of the box, the dimension of the total box where the electron will move, then you change the energy. This is in a simple way what's called nanotechnology. One common misconception happens to, a long time ago, which called Schrodinger cat. So they say, mocking this concept, saying that if you put a cat in a box, now it's a particle in a box, and if you hit it with some kind of a gun or laser, then, it's 90% died, 10% alive, some kind of probability, and how it could be possible. This is not under, this concept comes from the wrong title. It's not a particle in a box, it is a wave in a box. If the cat can behave like a wave, then in this case, if you put it inside a box, it will become like a wave, a standing wave. This will happen only if the cat's speed is very fast. If the cat's speed is similar to the speed of light, and then you put it inside a box, it will become like a wave. In this case, you might get this phenomena of life and death. But of course, if the cat moves with that fast speed, most probably it will be dead by arranging to that speed. I think the life cannot remain with this very, very high speed. So the concept of died here is, comes from my misunderstanding. We are not speaking about particle in a box. We are speaking about a wave that confined to some kind of a space. Then the energy are affected. Then the energy are affected by the dimensions. Of course, this is N, the energy level. This is H, Planck's constants. This is M, the mass of the particle. And this is the most strange part. It's the length, which means the dimension. In case of the classical, the energy is equal to minus, some kind of a half mv square, which means it also has m, it has a speed, but it doesn't have any effect of the surrounding. Here, the energy is affected by the surrounding, by the size, by the dimensions of the box. So the energy itself is changing regarding to the, confined space. In another way, if you confine something inside a small space, then the energy levels are defined. So the concept of quantization or energy have some discrete values like n equal 1, 2, 3, it cannot have 1.5, comes from what? It comes from the confinement, the putting the particle inside some space, confined space. In this case, it have only possible solutions, which is the standing waves. It cannot have 1.5 wave, it have only 1 wave, 2 wave, 3 waves. So it can have only, specific numbers. Otherwise, it will vanish itself because it is a wave. So this is what's called discrete solutions. This solution with n equal to 1, 2, 3, 4 is kind of possible energy for such wave. And if the energy change, the particle will not move from one place, from level 1 to level 2. It will not move. The particle will just change its wave from this energy to the other energy. So it will simultaneously vanish from the first case, goes to the second case, because it's supposed to be a wave, and the wave just change its amplitude. Of course, if the electron transmit from one level to another, it might take some time because it still have some particle character. But if it is a pure wave, it's supposed to move from one level to another instantaneously. At the same time, can vanish from the first one, goes to the second one, because it changes its amplitude. It changes its wavelengths to fit the new criteria. Now, let's ask you one question. P orbital, we all know that P orbital has, three orientations, but in any of these three orientation, we usually draw it as a two loops. One of them with, some kind of shadows, other with not, maybe some kind of with color, other with different colors, and always keep asking my students, what's, the need to make these two loops distinguish from each other? Isn't it the same electron moving in the same orbital? Why, some of these loops are maybe red in color, one in blue in color? Why we should put some shadows here and some is not here? And, even these students might be in the master or the doctor degree, and I keep asking them this question and they keep giving me some strange answer, like, the probability of finding the electron here is more than here, or some kind of saying that this is the spin, of the electron. And, they try to invent some way of saying why this loop is different than the other loop. And they simply forget the basic concept. They simply forget what we are explaining. As I said before, we are dealing with waves. We are not dealing with particle anymore. So since it is a wave, any wave have what's called amplitude. As you can see, when you go to the sea, there are some kind of waves. It goes up and down relative to the sea level. The waves are higher and lower amplitude relative to the sea. So in a very simple way, if this is the sea level and this is the waves come to the sea, so in that case, this part has a positive amplitude and this part has a negative amplitude. So in that case, these two loops, the difference between them is just the amplitude sign. One of them is positive amplitude, one with negative amplitude. So you should, if you still don't understand this while you are graduated, it's a big shame, that you don't understand such very basic concept. And actually, this basic concept lead us to the more important part, is what's bond. The bonds, or the chemical bonds, are just overlaps between these atomic orbitals to form a molecular orbitals. So this overlap is just a waves overlaps together. And as in case of the waves, if the peak meet another peak, there will be a constructive interference. It will result in a higher peak. And as the same case, if this, shallow or whatever going down meets the same amplitude, a negative one, two negative will make a constructive interference. So constructive interference will happen if two positive similar signs, plus or minus, meet together. They will increase the intensity, constructive interference. And if the peak meet minus or trough, this plus meets minus, if two waves with different sign of amplitude meet together, they will vanish each other, they will destroy each other, result in destructive interference. This is what happens in case of the bonds, as we will see right now. So we have a 3D orbitals oriented over the x-axis, y-axis, and z-axis. If two atoms, like two carbon atoms, overlap with each other, means come too near to each other, where the wave orbital of the first atom sees the wave orbital of the second atom, and if these two waves come together, then if they are in the same, way amplitude, they will make a constructive interference. But let's see two different types of the orbitals we have now. One, of them, we have three p orbitals, as you can see. One of them will meet the other one head-to-head overlap, and the other two, will beat each other like side-to-side overlap. This results in two different type of overlaps, one called the sigma bond and the other called the pi bond. In case of the head-to-head overlap, let's say whatever, it's not to call it Bx or whatever, By or Bz, they are the same. But among these three orbitals, one of them is oriented in a way that when these two atoms approach to each other, the head-to-head overlap happens. So if these two of loops of the same amplitude, you get like sigma or bonding orbital. And if they are in different amplitudes, they will vanish each other. They will vanish the amplitude of each other, resulting in a node where no amplitude, no electrons here, which is called anti-bonding or sigma star. So both of them are sigma type or head-to-head overlap. While one of them, the amplitude gets bigger because of the constructive interference, and the other one results in destructive interference. This is sigma of lower energy and sigma star of higher energy relative to the energy of the atomic orbital themselves. The other two orbitals, p orbitals, when they come near to each other, they either get, with like similar signs. In this case, this one with this one will make a constructive interference, resulting in a pi orbital or in a different signs. Then they will, vanish each other in this area, result in a pi star orbital. So the star means in both cases, like sigma star, pi star, means anti-bonding, higher energy. And without the star, like pi and sigma, means bonding orbital or lower energy. If you sum the electrons in the bonding orbital minus the electron in the anti-bonding and divided by 2, you will get what's called the bond order. Isn't this simple example that we will see next? So if we have, like, for example, two oxygen atom, oxygen is in group 6, which means 6 valence electron, 1, 2, 3, 4, 5, 6. Tamam? This is the 6 orbitals of each atom. Then they will overlap with each other. So s orbital overlap with s orbital, either in phase or out of phase, making a constructive interference or destructive interference. Constructive means lower energy, lower energy. So this is the energy goes up here, up energy. So this lower energy then relative to what? The atomic orbitals themselves, which called sigma. And another one with destructive interference, which is higher energy relative to the atomic orbital themselves. This means this is stabilized, this is destabilized. So if we sum the bonding electron minus the anti-bonding electron divided by 2, because every bond takes 2 electrons, you will get number of bonds. So in case of p orbital, we already know now that the p orbital are 3 orbitals, but only of 2 types. One will make head-to-head, which means sigma and sigma stars, and two will make, the other type, which is pi and pi stars. Then you start filling these orbital 1, 2, 3, 4, these orbitals inside these levels. How many orbital electrons here? 1, 2, 3, 4, 4. So, and the other one here, 4. You put 1, 2, 3, 4, 5, 6, 7, 8, which is, the same number of electrons, but you fill it from down to top. In this case, as you can see, the compound is paramagnetic because it has unpaired electron. And the most important part is that the bonding electrons, these sigma and pi's, and this is anti-bonding pi star and sigma stars. So the total bond order is equal to 2, means the O is bonded to the O with double bond. From this concept, we can see that what is the stability of O2 plus? O2 plus will have, one electron is missing. We raise one electron from here, which reduce the number of electrons in in the antibonding from 4 to 3. Then the bond order will increase to 2.5, which means the O2 plus are supposed to be more stable than the O2. This is relative to what's called bond order. The same concept of overlap can happen to different types of orbitals. So for example, if an S and B orbital overlap with each other, of course S is small and B small. If S and SP orbital overlap with each other, we will have what? What do you expect in this case? Don't forget that the B orbital has two types now. Of course, it's three orbitals, but it has two types. One is standing like this, and two will be in, this parallel position. So one like this, and another third one is from down to up like this. So let's see which of them, what will happen to the S orbital in each case. In this case, if we try to make these two atoms near to each other, so their, wave overlap, what will happen? As we can see, these two similar colors means similar amplitude will have a bonding or constructive interference, and this different colors means destructive interference. So in this case, the constructive interference and the destructive interference are of the same amount, so the net will be 0. So in that case, there will be no overlap, because regardless of the distance, make it small, nearer, farther, in what distance, in any distance, the amount of the bonding overlap will equal to the amount of anti-bonding overlap. So the net overlap is 0, means the energy will remain as the atomic orbitals themselves. So this is called non-bonding orbitals. So you will get a non-bonding orbitals, or orbitals doesn't have any chance to make lower energy or higher energy. They remain the same energy as the atomic orbitals themselves. Then in this case, they called non-bonding orbitals. But in case of the other two type of, the other B orbitals, the other two, which has the type of head-to-head, then we might have, these two of the same sign making a bonding overlap, or of different sign anti-bonding, results in what's called sigma and sigma stars. So either non-bonding or sigma and sigma star for case an S with the 3 B's, which mean one of these B's will result in non-bonding, the other two will result in sigma and sigma stars combination for each of them. You can, of course, now expect that the bonding is just an overlap, as we explained, and we will continue explaining further facts for you to understand the basic concepts of computational chemistry, because as you can see, we don't care so much about the equations, but rather we care about the physical meaning behind such equations. Because we will use the computer to solve the equation, we need to understand what's the results comes out of this. So that's enough for our videos today, and we will continue further for the reviewing of some other concepts that's necessary to understand computational chemistry. Thank you for listening, and let's meet in the next video.